You hear me? Hello, everyone. Thanks for being here today. It's a pleasure to meet you all. I am Jorge Castillo. I'm going to be talking about functional Android today, or how to use the functional concepts for writing functional apps. Thanks for attending, and thanks to the Android Summit organization for letting me be here today. So let's jump right away into content. So the first thing I would like to clarify is, or what I would want you to wonder is whether we would like to use functional programming or not in our Android apps, because we are used to different paradigms in this platform, and we've been using object-oriented and imperative programming since ever. So what would be good reasons for starting to think about applying the functional concepts here? Well, a good point is this mantra, or this idea of trying to achieve determinism over our logic. So we are going to be using our this idea of pure functions, which are functions that at the end of the day return the same results for the same inputs. So they are predictable, they are easy to test, easier to reason about, and that's one of the biggest pieces, or the most important pieces of functional programming. So that's going to bring clarity, remove ambiguity, and kind of bring determinism to this kind of chaotic world that Android can be, with all that inversion control and all that stuff. So we are also going to learn how to keep side effects under control in our apps, and we will learn why that is a good thing. So one of the important things that I will really like to cover is this idea of concern separation that we are going to try to achieve, and it's based on the idea of staying declarative and deferred as much as possible. So we want to have the chance to write our apps as basically as declarative, pure composed logics, and then we want to have a runtime for them. So we want to kind of decouple both worlds, be able to write our app as an in-memory description of what the app is gonna be, or how it's gonna behave, and then provide a runtime to actually run the whole thing, right? And when you do this concern separation, we get the chance to apply runtime optimizations, for example. So it's a really important thing to keep in mind. You can find a good example of this in the world of the Kotlin standard library, for example, with sequences. That if you're familiar with them, you will remember that they are lazy. They allow you to kind of compose operations on top of them using these operators that they give you. And then at some point you apply like a terminal operator that is running like the whole thing. And that's the moment where the system applies, or the runtime. That's like the runtime. That's where all the optimizations are applied, and so on, so on. So that's a good example of this concern separation that is already in the Kotlin language. But you can also see an example of this in Jetpack Compose, right? And let me explain what I mean by this. Jetpack Compose uses this idea of concern separation also. So it allows you to create this in-memory representation of the UI tree. So it's basically a series of, composable functions tied together, composing the whole description of how our UI is going to look like whenever we need to render it. But at that point, it's only like a representation in memory of these lambdas, these composable lambdas. And then there is a runtime that takes all this stuff that is retained in memory and is able to interpret the whole UI tree, providing those optimizations, right? And as you can, you probably already know, if you've been keeping an eye on Compose, you know that there is a lambda dependency, a runtime dependency that you can fetch and use for providing a runtime for Android, basically. So it's this idea of concern separation, where you use the composable functions to create this description of how our app is going to look like. But then those need a runtime to actually run them and to integrate this in-memory UI tree with our platform, in this case, Android. And that's what brings the opportunity for optimizing the runtime, because you can do things like running your compositions in parallel, even offloading compositions to different threads, or changing in what order they are going to run. And this is why they tell you not to run side effects inside of the composition or inside of the composables, because you need those to be pure. Okay. Right, so the composable function has actually a lot to do with how suspend functions work in a way. So if you think about how composable functions work, this is a description of a UI effect, basically. That's what you got inside your composable function. But those are also constrained in the sense of from where you can call them. So you can call them from other composable functions or from an actual integration point, which is the set content where we're going to feed all our UI tree inside. So this is again the same idea, right? And this kind of control we get when we write our UI as a declarative composed tree. Is basically the ability that we have by separating both concerns and being able to apply the runtime optimizations afterwards. But you want to keep control on where are you running those effects from. That's the overall idea of, and you want that to be compile time tracked. Okay, that's the most important thing here. So you see how it works in Compose. You get this set content call that you are gonna add in on the lifecycle callbacks when you want to create your views, and that's basically gonna be the runtime, which is gonna go over the whole in-memory UI tree, interpreting it at runtime and providing any optimizations required. And then you hook your UI tree inside of it. So in the case of Android, that's going to interpret the tree and going to provide support for the SKIA rendering system to kind of interpret that in-memory representation of UI and kind of yield what the SKIA rendering system needs to render stuff on screen. So this idea should allow us to keep runtime decoupled from our actual logics and even swap the runtimes. Right? So we should be able at some point to provide runtimes for the web or the desktop or things like that. But can we use this concurrent separation concept in the world of the Android architecture? Yes, we can. We can do it. We can use suspend for that. So it's pretty much like the same mental mapping we need to have. So you have suspend. Suspend is a standard library keyword that the language provides for flagging effects. So you want to use it for flagging, potentially blocking, long-running computations, all those kind of things that represent effects. So whenever you flag them, you are going to make sure that the compiler keeps track of how those are used and keeps track of the fact that they need to be used from the correct environments or called from the correct places in your architecture. So if you suspend an effect, what you're going to get in return is the compiler awareness for detecting how you're using that side effect and from where you are calling it. And it's not going to allow you to call it from anywhere. You will need to provide proper environment or context to run the suspended program, which is going to be a coroutine or another suspended function. So this is how we can leverage the power of the compiler to kind of detect and keep track of how we use the side effects. So we are sure that anytime we want to call a side effect, we do it in a way that is under an environment that is prepared for it, basically. So let's start using that concept to build a simple Android architecture. Let's say we have some services, persistence, error trackers. We're going to flag all those functions that used to be like on the leaf nodes of our architecture. We're going to flag those as side effects. So we are going to flag those as suspended computations and keep moving. So that's going to make sure that they cannot run anywhere, but they need an actual coroutine, an actual environment prepared to run effects. But for that, I mean, if you keep doing that, you will see that you will need to flag all your computations in your call stack as suspend, because that's going to crawl up your hierarchy up until the actual integration point or the point where you are creating the actual coroutine. So, well, that's fine. That's like a staying declarative for your whole execution tree. That's how you are going to achieve purity, because that's going to ensure that you need an actual runtime to run the suspended program, and that's where you will be able to apply optimizations one more time. So suspend is giving you that, but then you will need to provide an environment to run the actual suspended program, because otherwise you cannot really run it in Android, because Android doesn't really provide support for suspended entry points, for example, like those suspend main functions or those I don't know, like the suspended endpoints you can declare in Ktor. That's not something you can do in Android. The lifecycle callbacks are not suspended, so you need to provide an environment to run a suspended program. You need to create a coroutine. So thinking about how we do that today, if you think of, for example, the calling Fx Coroutines library, we usually use these coroutine launchers like launch and async functions, which at the end of the day are creating a coroutine that is going to run some suspended program, and that you can also tie to a lifecycle scope, and use all that stuff of that calling Fx Coroutines provide for structured concurrency, cancellation, and everything. But you need to provide that coroutine. You need to provide the environment. In the case of functional programming, there is the Arrow Fx Coroutines library that is equivalent in a way. So it's a fully fledged framework that allows you to write complete programs and programs that contain effects and need to switch threads, switch context, do any sort of concurrency tasks, anything. You can do anything that you will do with, for example, calling Fx Coroutines, but this one is going to be opinionated towards the functional ideas. So in case you are trying to apply the functional concepts to your app, what I am suggesting is that you use Arrow and use Arrow Fx Coroutines instead of calling Fx Coroutines, right? But both are pretty valid. It's not like you can use calling Fx Coroutines to write Android apps or anything like that. It's more like, what's your choice in terms of the programming style or the paradigm you want to use for your app? Well, if it's functional, you will go for this one. So Arrow Fx Coroutines provides an environment so we can run our suspended programs, or in other words, our effectful programs, which is basically going to be our pure logics, because everything stays suspended waiting for an environment to be run. And then you can see how you can hook it at the different entry points you have in the system on the lifecycle callbacks. So you create an environment, and then it provides like different execution strategies for your program. So you can keep your declarative in-memory representation of the program, which is like your suspended program, which is pure up to now. And then you can run it using different strategies: synchronous, asynchronous, asynchronous, and cancelable, and different ones that we will also peek into around the end, close to the end of this talk. So we will know a little bit more about this. In this case, we are using the callback one, but yeah, it's just one of the alternatives available. So you can wrap your suspended program and then use callbacks for the errors or the actual successful result. So if you want to handle errors that might have not been handled yet by the application logics, you can do it here. So maybe you can want to track those into a network error service or something like that. So, okay, you are going to hook that in the lifecycle callbacks, basically because Android doesn't provide suspended entry points. And that's where your logics are going to be hooked from, your pure logics. So we have this environment, we have this runtime we need to provide for running our suspended or effectful programs, how to write the actual logics that compose those programs starting from there, or how to write like the complete architecture. So we are going to be using the power of data types, and the main one we are going to focus today on is either, but we'll also see validated and a few more. But basically the idea is that we are going to use data types as a way to raise concerns we have over our data, okay? So I'm not sure if you're familiar with this idea of railway-oriented programming, but it's basically the idea of understanding programs as a composition of functions that can either succeed or fail. So you have this disjunction for each one of the computations. So this is basically what I'm talking about. You see this graphic. So imagine your program is a single pure function or a single function that can either go well and stay on the happy path, succeed, or it could go wrong, and then we would get on the error path or the error track. So you can imagine a program as a composition of those functions, right? Well, I'm going to share after this talk. Please remind me to do this, but I want to share these links on the Slack channel that you've got for this talk in the Android Summit Slack channel. So I don't think all of you are there. So maybe I will ask my the staff members to enable the chat again if possible. I'm not sure if it's possible in the Zoom call, so I can, yeah, they are going to help me. So I can also share it there because I'm seeing that you are all there and it kind of makes more sense. Everyone, there you go. Thank you very much. Okay, so you got the links right there in the chat, so you can peek into this idea later on. Speaking about either, we want to use either for kind of encoding this disjunction, right? Because any computation in our program is either going to go well or fail. So we want like to make that explicit in the return types of our pure functions across our architecture. So the idea is that we want to use either for computing over the happy path and then still have the chance to plug error handlers at different levels, depending on how we want to organize error handling in our app. But the main idea is to keep that disjunction as explicit as possible and also kind of enforce us to treat both sides so we don't forget. So in that sense, our program is going to be more complete. Right, so encode either is basically a seal class with two possible implementations, left or right, and then it has some operators like map, flag map, and so on. So you can imagine, I guess you can imagine how it will look like, more or less. But the idea is that we are going to put our errors on the left side by convention, and the success results on the right side, or the success values on the right side. This is by convention, and this is also because the either is what we say biased towards the right side. The right side is like the happy side of either, like the happy path. If you put something on the right side, that's how, that's where operators like map and flag map are going to be working with. So if you have an either that is a right, and you map or flag map, those mapping lambdas are going to take place over the data and keep going. But if it's an error, those are not going to do anything, but just forward the error right until the end. So when you do this, you kind of get the chance or the ability to keep computing over the happy path, because that's only how flag map is written, just by using map, flag map, or any of those combinators. Plainly because they are biased toward the right side. If they find that the either is a left with an error at that point, they will just forward the error, and the result of the overall computation will be the actual error in the end. So you get an either. Let's say we have a function that in this case is returning a stubborn either value that could be a right containing a valid or a successful value of a user, or a left with an error. And then you have this fold called for providing lambdas and processing both sides, right? So whenever you want to apply effects, depending on the side, or kind of process what's inside of either, you're likely going to use fold, and then you will be forced to pass the two lambdas. So you kind of don't forget about the error side either, right? Either is also able to encode a way to handle nullable data. We had this conversation in the Arrow team as an Arrow maintainer that I was also part of with a lot of people on the team, that was this idea of a deprecating option, because we were providing these, the standard option data type for representing the idea of presence versus absence of a value. But we decided that there was some kind of redundancy there because you already have the Kotlin nullability or nullable modifier. So you can use that one to work directly over nullable values without any sort of wrapping. But even though if you want to use the option style or the option like style, which is kind of monadic in meaning that it provides methods like map, flag map, so it's kind of better for compositionality probably. So in that case, you can use either. You can use either from nullable, which is just a constructor method and the companion object that you can use to lift any nullable value into either. So let's say this load episode might find the episode or not. So it's returning a nullable episode. You can lift the result into an either using from nullable, and that's going to return an either left in case it's not found. Actually a left of unit, because in this case we don't need more semantics. There is only, like, let's say a single type of error. The value is not there or it's there. So in that case, you will get a left of unit, but if it's there, you will get a right with the actual episode in this case. And in that case, you will be able to map and keep computing, because map is part of either. So either is biased toward the right side. So in that case, the map will take place and map it to the characters, right? So that's why we get a result that is either going to be the actual error or a list of characters in the end. So there is also obviously good integration for third-party APIs. So you are using the usual third-party API that kind of propagates errors as exceptions. You are going to have the chance to use either catch to wrap it. Either catch is basically expected to wrap suspended effects. So you can put any suspended operation in there, and then you are going to get the result lifted into either automatically. So if it's a successful result, you will get an either right with the value, but if it's an exception thrown, you will get an either left containing the exception or wrapping the exception. Then you can use the map left function for kind of strongly type your errors. If you want to map that throwable, you go into something else. So this is going to be very useful in Android because we are really used to kind of strongly type our errors using like a sealed hierarchy of errors in our domain. And we want to strongly type them as soon as they enter our domain. This is going to be a good option because you can wrap any suspended computation into either catch, then map left to map the error and strongly type it to any strongly type, any strong error types you want to use in this sense. A point on this is that either catch is also suspend, and it's suspend because it's expected or is meant to be used to wrap side effects. Okay, so whenever you want to use it, since it's suspended, again, we are enforcing you to provide a proper environment to run this program because it's an effectful program. There is a question in chat. Do we see in other FP languages the same preference of using either instead of option? No, this is something that we find in Kotlin, only in Kotlin and particularly in Arrow, because Kotlin has this first class support for nullability that you can't find in other languages. So if you are thinking on Scala or Java or other languages that don't leave this nullability concept as a first class citizens, those are providing option implementations. But in this case, we thought that it wasn't really required, given we have the nullable support at the language level. And in case you still want this monadic style, you can just use either, which is just a disjunction, the same way option is. Like option is like either absent or present, so you can model that using either. So for composing logics, you can just go for either flat map and keep moving with that, right? Because flat map is how you compose operations or chain sequential operations using data types. So in the case of either, let's say we have a program with two different dependent computations where you run the first one and then the second one. Keep in mind that you should only be able to run the second one if the first one completed because they are dependent. So let's imagine that the second one requires the result of the first one. This is where something important comes into play, this idea of failing fast or short-circuiting errors, and that's how either flat map works. If you have two operations and you need the result of a previous operation to run the second, of the first operation to run the second one, you cannot really run the second one ever if the first one didn't succeed. So in that sense, you can save the computational time of the second one. So you can imagine that if you have the standard program where you have an effect, you wrap it into either catch, and then you start flat mapping over it to compose like the whole, let's say the whole algebra or the whole execution tree in memory of how your program is going to behave when it runs across all the layers, because we are very used to use the different layers in Android, and you can imagine that you could perform your request, then map the errors, then flat map that into something for the repository layer, then flat map into something, some logic for the use case, like it crawls your hierarchy up. But what you get in the end is an amount, a dynamic amount of flat maps over either that compose your whole logic for a given use case. And in that case, you cannot really perform any further computations that are requiring a result of a previous one in case that one failed. You cannot just keep computing. So in that case, either is just going to short circuit the computation and return a left, as we saw before, right until the end, because that's how flat map is written, because either is biased toward the happy path, as we said before. So you see that in this graphic. You see how you have the first computation, that one fails, and then we stay on the error track right until the end. Because we don't have the result of the previous one, we cannot really perform the second one. So we can also save the computational time of that one. So how does that look in code? Basically flat map. So you can run one of them, you flat map and run the second one. So if the first one never succeeds, this flat map is not going to take place, but the actual error is going to be returned as the result of this composed computation. But you can write that using the bindings, or what we call the bindings. This is based on the idea of the monad comprehensions that come from other languages like Scala or the do notation from Haskell, but it's this idea of writing these wrapped computations that are going to return a value into either. For example, in this case, you want to be able to kind of automatically unwrap the value on the left side and access it on the next line, like if it was synchronous, without the need for an explicit unwrap or anything like that. And you are still inside of this either context all the time. So the idea is that you can write this that is equivalent to flag mapping, because every time you bind, this is a binding, every time you bind over an operation that returns either, you are able to access the result on the left-hand side synchronously, and then you can just use it right away, the actual inner value of the either for the happy path, right away in the next line. And that's a synchronous style that we are enabling thanks to the power of coroutines under the hood. But it's basically allowing you to work with sequential computations using either that are not without providing explicit flag maps. You can imagine that all this is translated to a flag map chain under the hood using an annotation processor, which is part of Arrow Meta, that is going to be converted into a compiler plugin at some point. So this is just a syntax sugar. This is an alternative syntax you can use for writing sequential computations, right? That are using either. This is why we need to provide this either computational block, because it's like, let's just start writing our either program, or our program that is based on either computations. And then you start running your either computations, binding, assigning to the left side, then using it on the next line sequentially, then binding for unwrapping the result, and so on and so on. So you can go more complex with this, but stay under this like one level of indentation style or synchronous-like style, and keep chaining more either computations. Like in this case, we have 3 computations. Sorry, this load speaker, load dogs, and load event. So in this case, let's see how fail-fast works. If you get an error or an exception thrown on this either computation, that will be catched as an either left, and that's going to short circuit the whole thing and return the actual left of error in the end. So you will not actually perform any of these 2 computations anymore, right? And that's only because it's using flag map under the hood, and again, a flag map will only work if it's a right value, or we stay under the happy path, which is not the case here. So left of error, that's going to be forward, then right until the end. That's the result of the composed computation. So that's for sequential computations. But what happens if we care about all the errors possible? Because if we are talking about dependent or sequential computations, it's impossible for you to kind of accumulate errors in a way, because if you don't have the result of the previous one, you can never, the previous one failed, you can never run the next one in the chain, meaning that there's always a single error that is forwarded right until the end. But if you really care about running, about accumulating errors, that's only possible in the world of independent computations. Let's see an example of this. But we are going to be using validated. Validated is similar in a way to either, but it's going to give us the opportunity to accumulate errors on the error side. So in this case, there is a type alias that is called validated nel. Nel stands for non-empty list, which is basically a validated that is able to accumulate errors on a non-empty list of errors for the error side. So this is going to give you the power of keeping this disjunction between data that you consider valid or not, but at the same time accumulate errors on the left side. So let's see how that looks in code. So it feels like a bit like a wall of code, but imagine a couple of independent computations, that might go to network or something and load some data. We are going to validate catch nel, which is similar to either catch, but in this case it's going to lift the result into validated nel. And let's say those computations throw right away. Like this is totally stacked, but imagine this goes to network and throws or something like that, or to the database and the connection fails or something. And then we are mapping the errors to strongly type them at our domain with some, predefined errors we have in our error hierarchy. So yeah, we have a couple of independent computations. Let's see how to run them independently and gather errors and results in the end. So to do that, the first thing you want to do is create an error accumulator. And the error accumulator, you can create it using a semigroup, which is A semigroup is a type class, which is just like a behavior, a generic behavior that works over a generic type. And in this case, the behavior it defines is the combination behavior for that given type. So in this case, you are defining a combination strategy for the error type or an error accumulation strategy. And it's going to be over a non-empty list, right? So it's going to accumulate all the errors in a non-empty list. So you create your error accumulation strategy using a semigroup. And then you can use the applicative, which is another type class, which is a generic behavior providing tooling for running independent computations like this tupled encode. So you use the applicative, you pass the actual error accumulation or the technique or strategy, the accumulator we created, then you can already call tupled end over it and provide all your computations. That's going to return valid or invalid depending on the case. If it's invalid, it will contain a non-empty list with all the errors as you see here. And if it's a valid, it will contain an actual tuple with all the results together. Okay? So you can imagine you can use this for data validation, but you can actually use this for any kind of data you want to accumulate errors for and run independently, right? It doesn't, even if it's data you're loading from network or whatever, you need to think about this more in, not like for the semantics of validated, because you can also validate data over network, but more like for what you achieve using it. So you have like multiple different independent computations that are like network computations, and you want to gather results in the end, you can actually use validated for that. But the problem, that's not totally true, and it's not for either, because those data types are eager, meaning that as soon as you create a computation using either, with either catch, for example, or validated, the computation is going to run. So you need a mechanism for ensuring that those stay declarative and deferred. And we have the chance to represent all our execution tree in memory and then come later on and provide a runtime for it. This is the idea we were talking about in the beginning. So we need to flag those computations as suspend. That's going to make sure that we need to provide an environment to run our suspended program. And then you can go from there. But what about threading or concurrency? Because we are not covered yet in that sense. What would you do if you want to offload these computations? So that's where Arrow Fx Coroutines library comes into play. So basically the library is like a functional concurrency framework. So it's going to provide you like a lot of functional operators for running suspended computations. So you will be able to do things like repeating or retrying suspended effects based on a complex, reusable, and highly composable policy. You will be able to parallelize requests. You will be able to use resource safely across time, or like a lot of different ideas that you could be, or raising different suspended effects, even though a lot of different concurrency patterns that you will need to write a lot of code for supporting that are going to be running suspended effects. And those all those operators are also suspended by themselves, meaning that since those are meant to run effects, you are not going to be able to run them outside of a prepared environment for running effects. One more time. About cancellation, all those operators check for it automatically. Okay, so if you get the parent coroutine canceled, the children jobs are going to get canceled automatically and everything. So let's have a look to some of those. So the environment, this is something we've already been talking about. It provides different execution strategies. It's part of this Arrow Fx Coroutines library, so you see how you can use it to run your suspended program using in different runtime strategies or execution strategies. So you can run it synchronously or asynchronously, or even asynchronously and cancelable. So you keep a cancellation token you can invoke later on for actually cancel your whole program and all the children jobs pending from that, or kind of hanging from that one. But it's an actual interface, the environment. So you could provide your own environments or your own runtimes if you wanted to. If you want to offload tasks to a different dispatcher, which is something really common in Android, you can use eval on for that. So you can basically fit any suspended effect inside of it, like this one, either catching or whatever. Actually, any of the Arrow Fx Coroutines operators, because all of them are suspended, you can offload them to a different dispatcher using eval-on. Cool point on this is that it's going to automatically get back to the original dispatcher or the original context as soon as it's done. So this is going to become very handy in Android, for example, that we are very used to kind of offload a task of the main thread and then get back to the main thread afterwards. This is something you could use for that. There is also methods for parallelization, as we said. So you can run n parallel effects, like in this case, 3 effects or 3 suspended effects, and then gather results in the end. So it works like that. The cancellation works like automatically from parent to children. So if the parent coroutine that is running this, which is likely created by the environment probably, if that one gets canceled, the paramap call will get canceled and all the children get canceled. But this paramap operation is actually meant to gather all results in the end, so all results are required, meaning that if there is one of the children failing, throwing, the rest of the children are automatically cancelled also. There is the partable then counterpart, which is the same thing, but in a synchronous-like way. So you kind of use the power of coroutines under the hood, and you can just get the result as a triple, in this case, as a tuple, with that amount of elements provided by the amount of tasks you are running, and then you can access them right away on the next line synchronously. Again, you're running tasks parallelly and joining results in the end. So this can be very useful, like for example, you have a database, you want to compose a combined model out of models that you are storing in different tables or something like that. You could run those suspended effects parallelly and then gather results in the end to combine them into a composed model. Cancellation works the same way, from parent to children, same ideas. If you have a dynamic amount of suspended effects, you also have part traverse for that. So it's good for if you got a collection of elements and you want to run one effect for each, like in this case, we go to the service to load an event by these IDs. So we are running like one effect for each one of the elements using part traverse on a given context. All of them are going to run parallelly, right? And you're going to get the results as a list of elements in the end. So this is really cool for when you don't really know the amount of elements or the suspended effects you have. You can use part traverse for going over the list and running one effect for each one of the elements. And the same way there is parse sequence, which is just an overload, but for a list of suspended effects. It's going to run all of them in parallel and gather results in the end. You can also raise suspended effects, so you only keep the winner. So what you get here is basically fold operation. You can run n parallel suspended computations and then you're raising them. So you fold, and then depending on the winner, one of the lambdas will get called, okay? Cancellation, again, from parent to children, it works the same way. You don't need to worry much about that because it's going to be the same way in all the different operators. In this case, you keep the winner and the losers get cancelled because it's this use case where you don't really care about the losers anymore. You only care about the first one that completes. So there is a good use case for that. For example, to give you an idea, you could use that in Android. Let's say we want to scope a long-running task to the Android lifecycle. So for example, what we do is using this suspend coroutine wrapper from the standard library for wrapping actually a lifecycle observer that is going to be only resuming the program whenever there is an on-destroy event happening or taking place. So this is basically our way for wrapping, or the standard coroutines way for wrapping an Android callback or any callback API, which is going to return a suspended computation that in this case will stay suspended until we finally get an on-destroy event. So you have that as the initial computation to race against, that is going to stay suspended there, and then you can have your long-running computation for loading some data, for displaying it on a screen or anything like that. So you could go to your activity, and after you provide the environment that is always required for running suspended programs, you will be able to raise both. And automatically, if this one happens first, as soon as it emits an on-destroy event, it will resume the computation and it's going to cancel the other one automatically, or the other way around. So if this one completes first, you are done, you can cancel this one and just release the actual callback. or the actual observer in that case. This one is really cool because Arrow Fx Coroutines also provides a mean for retrying or repeating any suspended computations based on a complex policy and highly composable policy. So you can use this retry call providing a policy for retrying basically any suspended computation. So you can fit in here any other Arrow Fx Coroutines effects or operators. And see how you can build this complex policy. You can create, for example, an exponential backoff one that starts on 10 milliseconds and it has, I think, a default growth factor of 2 or something like that, but you can provide your own one. It's just an implicit parameter, a default parameter, sorry. And you want to do that, keep using that exponential backoff while the output stays under 60 seconds, and then whenever you are over that, you want to space up to 100 recursions every 60 seconds, for example. So it's a complex policy you are building there using this DSL that will return an actual schedule, and you can use to retry your suspended effects as much as you want based on the policy. This is cool because it returns a data type that is this schedule, and you can kind of inject that using your dependency injection system, for example, and apply this same retry schedule in different network calls across your architecture, for example. And the cool point is that you have a single point where you're defining your retrying policies thanks to this. So you can just test that and make sure that it's going to work for all the cases, regardless of where you are using it from. For error handling, you can use this either catch, validated catch, nil, any of these kind of wrappers for building your computations over your suspended side effects or your data types over your suspended side effects. Basically because all the operators are suspended, so you can fit this into any of the operators or wrap any of the operators using this. So it's like very idempotent. So we got the tools for writing our effectful programs. We've got the tools for separating this concern of algebras or our pure logics that are suspended logics and the runtime. We got the tools for, representing this disjunction or railway-oriented programming for representing success results or errors. Also, all the concurrency tools. We are very close to be able to write a complete Android app only with these tools we've been taking a look at. But what about the streaming? What about functional reactive programming? Because the streams are also a big part of Android nowadays. Basically because of this strong inversion of control we have and this event-based nature of the platform. So you get events like for lifecycle, user interactions, application state updates, a lot of events that you can kind of understand as a streams of events, and then that you can compose all together as a single stream. So you can represent your app as a single stream as a composed stream of events. So, for example, these unidirectional data flow architectures usually focus on this idea of reactive programming or even functional reactive programming. So we make sure that we can bring some determinism to how data evolves and how the events flow across our architecture. So we are going to need a solution for emitting multiple times, embedding suspended effects, because otherwise I wouldn't really consider them functional streams. So that means that they need to be really compatible with all the Arrow Fx Coroutines operators we've been showcasing, which was just like a minor subset of the ones available. There are many more, but it's impossible to cover all of them today. But all of them need to be supported. Any suspended effects need to be supported within the stream seamlessly. We want it to be called, we don't really want those to be eager. We want to keep the power on composing, on staying on this declarative side, so you can keep composing operations over the stream and then keep that trigger so you can pull it for actually consuming the stream later on, which is a terminal operator, right? And that's going to be the runtime. So we keep this idea of concern separation. And we also want it to be highly composable. So we are going to be providing functional streams with this an implementation of the functional streams by Arrow Fx Coroutines. And those are going to be what we call pool-based, meaning that it's like the receiver, the one that is pulling elements from the stream, and whenever there are no more elements, it's going to suspend itself, waiting until there's a new element. So in that sense, And if the emitter emits elements too fast, you can use a queue to kind of avoid losing any of those elements and then keep consuming them at our own pace, or at your own pace. So this idea of being pool-based kind of removes the need for very complex back pressure techniques, because just by nature there is no way that you want to consume and you cannot do it at the right pace. So these streams can embed effects, meaning that you can use a stream effect to embed any suspended effect. In this case, it's a simple print. You'll see examples of this in a second, more complex ones using other operators. But you can imagine you can fit any suspended computation in there. The cool point here is that the result is emitted over the stream as soon as it completes. So what you get there is a description of an effect that will take place whenever you start consuming the stream, but not before. Again, we stay under the declarative world. And then you need to provide a terminal operator to consume it, like this drain we got here. That's the place where you convert all your pure declarative program, which is suspended, into an actual unsafe thing that is finally running all the side effects on it and everything. Any errors, if you have any failure, any exception thrown in those effects, it will get automatically raised as a failure into the stream, so you have the chance to recover using some operators available for that, like handle error width. So another example of embedding effects, you see how you can wrap your paramap computation into a stream effect, and then the result of these three parallel operations is going to be a combined model that it will automatically emit it over the stream, and then you could even keep computing on top of it, like adding flat map, or any other operations on top of that, right? So this is a big power, because any of the Arrow Fx Coroutines operators, all of them are suspended. So again, we can just evaluate them as part of our stream, so the result gets emitted over the stream. About threading, we are very used to have these observe on, subscribe on operators, where you kind of work over a given dispatcher or over a given scheduler for the upstream or the downstream, and you stay on that one. All that is not present here, because if you think about the actual definition of streams, it's only about emitting and observing, and there is nothing about threading, so it's more like an addition. So for achieving threading in the world of functional streams, you got our Arrow Fx Coroutines again, so you can actually use eval on here or paramap or anything you want for offloading your actual effect inside of the stream, and you do that in a very atomic way, so you only offload the actual suspended effect at that point, and then come back to the original context or whatever you want to do. So for composing streams, you can use part join. You create a stream out of streams, and then you can call part join unbounded or part join with a maximum amount of threads, depending on how many threads you want to use. And all the streams are going to run in parallel. So as soon as you subscribe or consume the resulting stream, you will be consuming all of them, and they will be emitting as soon as the values come. So you can get the results, for example, here in different order, because they are running parallelly. We can also wrap asynchronous APIs, callback-based APIs. So you can basically use this stream callback to wrap a listener that will emit every time it gets called, and then we attach it to Android like this on refresh listener. And there you got a stream out of refresh events automatically. But you can use the cancelable variant of it, which is basically the same, but it's going to require you to provide a cancellation token in the end that you can use for releasing the listener or whatever it makes sense for you to avoid leaks. So that's probably the preferred variant. There is also bracket. Bracket is a way for scoping resources to the lifespan of a stream, meaning that, for example, you need to work with a file, you provide lambdas for opening and closing the file, and then you can keep computing over it. And then at the end, whenever the stream terminates or gets canceled, the resource is automatically going to get released out, for you. So you can imagine that you would be able to use this for things like WebSockets, databases, files, or anything that you need to work across the life cycle of, or the lifespan of a given stream. The stream is going to take care of that, or the stream bracket call is going to take care of releasing that in the end, so you don't really leak the resource. All the relevant operators, you have things like map, flat map, effect map, if you want to chain different side effects or different suspended effects. all that standard stuff that we are very used to. Also handle error width to recover with another stream, and whatever. And then finally, whenever you want, you can call this terminal operators like drain, for example, for consuming the stream. So before that, you stay declarative, and at that point, you become, you kind of interpret the whole in-memory program and actually run it. There are ways for terminating or interrupting a stream given another stream. So as soon as this one emits, the big one is going to get interrupted. So you can imagine that we could wrap a lifecycle event using a stream callback or a stream cancelable, as we saw before. And then you can raise your program that it can be a stream with that other one. And as soon as this one emits, the other one is going to get canceled. For example, if you want to scope your streams to the lifecycle, this is a way you can do that. And finally, to consume streams safely, again, you want to do it using the environment, right? Any of the terminal operators in the streams or in the functional streams of Arrow are suspended also, because that's the point where you actually run all the side effects and you stop being declarative and pure and all that stuff. So at that point, you want to do it inside of an actual environment. The same way you will consume, for example, a calling as coroutines flow from within a coroutine, because otherwise you are not allowed to. Same idea, okay? In this place is where we want to consume the stream, so we are going to need to provide an environment for consuming it. And that's all I had for you today. So I know it was quite long, and I know that I kind of exceeded the time I had a little bit. Sorry for that. But a good point on Android Summit is that we got different rooms for all the talks. So you have the Slack channel for any questions. So I'm going to stay there for a while if you want to ask anything. It's a good moment to do so. Otherwise, we have the Kotlin Lang group where we have the Arrow channel where we try to provide always support for all the questions you can bring for your use cases or whatever. The maintainer team is always trying to help in that sense, okay? There is, if you want to expand on this, there is a functional Android course we are offering at 47 degrees. So you can take this 2 days course, which is like 16 hours, where we are really going in depth about all this because it's a lot. I know it's a lot. I just wanted you to have like a sneak peek on everything, but you can do that and book it as a group, like for a group of friends or your company or your team or whatever. You got that one there. And there's another one for functional programming fundamentals, which is another 16 hours course only over Kotlin and functional programming, not Android. So you have kind of both options there. So any questions that you want to ask? You have the chat, the Android Summit channel, it's called session chat D1S1T3. So that's the one for our session. You also have the chat in this Zoom call. But if you don't want to do it right now, because I don't see like a lot of activity right now, don't be afraid. I mean, just feel free to post your questions there. It's going to be fine. I will be there for a while. Thank you very much for attending. It was a pleasure. Goodbye.